quantum computing would be a potential threat for cryptocurrencies if they still based on these classical encryption schemes, which are vulnerable against fault-tolerant quantum computers.
Welcome to the first episode of The Beginning of Infinity. It is an AI quantum podcast. I strongly believe in a statement that you are an average of five people around you. Therefore, I started to meet different founders, tech experts, and gained a lot from it. So, what I thought was, why not record it and put it online so that even you all can gain a lot from it? Therefore, I present to you our first episode of So today, as our first speaker, we have Mohammad Yassin Farjani. He's a quantum researcher at QB, and he's also a founder and coordinator at Q Tunisia, which is affiliated with Q World. It's a community that works towards implementing quantum technologies, performing research around quantum, and bringing a lot of awareness around quantum. Isn't that cool? But what is more cool is the talk we had. We talked about how quantum impact cryptocurrencies, how they can break the current security, how the quantum internet actually works. Therefore, not taking much time, I am your host, Shubham Agnihotri, and you're listening to the beginning of infinity.
So I was just scrolling your profile, right, and I see that you have done huge amount of works in quantum. Like you have recently, not you have recently won the Qiskit challenge and the Q crack, right?
Yeah, I guess it's 1 year ago or 2 years ago. Mm, yeah,
So
it's
why?
guess get the global hackathon, or actually we won many challenges. Which one of them are you talking?
So it's like I've been a lot of challenges, but I don't exactly remember which one you're talking about.
Yeah, so there is Get the Global Hackathon. It was organized online at that time. It was COVID, and yeah, we got the first place. Me and my team. So basically, we developed the platform for making quantum experiments reproducible and shareable for developers and for researchers. And another hackathon is organized by Stanford and Yale called the Quantum Coalition Hackathon. And in that, also we got the first place, and we developed a quantum steganography protocol. It's a kind of cryptographic scheme using Qiskit. Yeah, and there are a couple of other hackathons. So, but those are
Your favorite ones or the highlight?
favorite ones. Yeah.
That's interesting. So, how did you end up in quantum? It's like because this is a field right now. It is what I believe is quantum is still at a very naive stage where there is not a proper fully functional quantum computer that can run for let's say even because I'm totally new to quantum, like I am exploring it, so maybe the question that I ask may be very naive to you, so just bear with me on that. So how did what was your inspiration and how did you get into quantum, and can you tell us a brief about your background?
Yeah, so I studied in my first year at university. I studied mathematics and physics, and then telecommunications engineering, specialized in network security, because I studied in Tunisia, and it's a 5 years program. So at my second year at university, I studied quantum mechanics, and I became fascinated by the world of small particles. At the same time, I like computer science and mathematics. 1 year later, I heard about quantum computing, and I say, oh, wow, this is a combination between computer science and quantum physics. And also, it requires a good background in mathematics. So I said, this would be my field. So, and since that time, quantum computing became my intellectual passion, let's say.
Wow, crazy. And so you coming from a research background, right? Right now you're working on. If I talk about your current profile, you're working as a researcher.
Yeah.
So what do you think is the power of quantum? Like it is still yet to be harnessed. Once we are at that stage. So what do you think it'll be?
So quantum in general can give us is powerful in security. So. And the only advantage that we have nowadays from quantum, I mean, in real world, is security. Like we can achieve a higher level of security, which cannot be achieved classically. And in quantum computing, maybe it can offer us more computational power. Yeah, so because in quantum computing, we are harnessing the properties of quantum mechanics. and yeah, that can give us a huge amount of speed up.
And so you were talking about steganography in your hackathon that you did. There was a steganography algorithm that you kind of made as a product. So for the listeners, can you tell us what steganography is exactly?
Yeah, so cryptography. I will start by defining cryptography. So the purpose of cryptography is to hide our data, or for example, let's say you would like to send a message to your friend, and you'd like to hide this message from any unauthorized malicious third party. So in cryptography, let's say we apply some mathematical function and functions, and we transform this plain text data, your message called plain text, to ciphertext. Ciphertext, which is the modified data or the unreadable data, which is protected. And steganography, we let's say upload our data and we hide it inside an image, or so instead of text, we can put our data inside an image and hide. So this is the difference between steganography and cryptography. Or maybe sound or music or something. Sound file or something like that. So not we are not hiding data in. We can like hide data in images, sounds, and many things, not only in text. And this is steganography is about that. Yeah.
So basically, let's say there's an image full of pixels. So in those pixels, you hide something onto the on it, or let's say, is it something that you add it onto the meta side or something like? Because as far as I know, what steganography is, because a brief about me, like I was a CH certified hacker.
Yeah.
And so like pretty much it's like you have the file size pretty much remains the same. So you add it onto the back end. And so how does that process actually works? Like if we get a bit more onto the technical side, like let's say if I want to create a steganographic file, so will it be like is it in the meta that it gets added, or how is it?
Yeah, so like it's like you embed your message or inside this image, and you encrypt it, and then you send this image file so that an attacker cannot even notice that you are hiding your data inside this image. So for example, if you send the normal message, the hacker knows that this ciphertext contains secret data. But if you send a normal image, the hacker sometimes cannot even notice that there is a hidden message inside this image. So yeah.
Got it. So because right now we are in an era where there's a lot of talk about quantum, and IBM recently there was a war for quantum supremacy.
Yeah.
And then there were talks around that once quantum is there in being, all the cryptography or security which is currently existing goes on a toss. How is that possible? Like right now, I guess for it was said, I guess, for SHA-256 or 512 or something like that, it takes around 10,000 years for a supercomputer to crack it, right?
Okay, so most of today's internet is secured using public key crypto systems, algorithms like RSA, elliptic curve, and we have a quantum algorithm which is called Shor's algorithm, invented by Peter Shor in 1994. And this algorithm can factor large numbers on a quantum computer. So let's give a simple example of RSA. If in RSA we have a public encryption key, and if you manage to factor this public encryption key into two prime factors, so RSA will be broken. And with Shor's algorithm, it's useful for factoring and also for discrete logarithm. And with Shor's algorithm, we can break elliptic curve and RSA. But the problem that the current quantum computers are not able to crack public key crypto systems, because we are in the NISQ area, noisy intermediate scale quantum computers. And maybe and to crack public key crypto systems, we need fault tolerant quantum computers with thousands of qubits. I hope that we can build these quantum computers after maybe 10 or 15 years. I don't know exactly But yeah, like we cannot break RSA right now, but in the future, with large scale quantum computers, it would be possible. Yeah.
Got it. So you said fault tolerance quantum systems. So what exactly are those? Like, what do you mean by fault tolerance?
Like, okay, I will explain something. Today's quantum computers are in the NISQ area. Like the most powerful quantum computers is IBM's one with 127 qubits, but these qubits are not perfect. So if you run a computation, you will not get concrete results because we have too many errors. But with fault-tolerant quantum computers, there are error-corrected qubits. We don't have too many errors. We can run computation properly on a quantum computer, and this quantum computer will have thousands of qubits. So it will be useful maybe for real world, and we can, let's say, implement our algorithms on fault-tolerant quantum computers. So there are quantum computers with thousands of qubits and with error-corrected qubits. Yeah. So we don't have this problem. We will not have the problem of errors with fault-tolerant quantum computers.
So basically, it's more like, we need to increase the qubits. Qubits can be, let's say, the number of you can in classical computing, it's basically the number of bits you add onto the system, and definitely calculations will cause some quantum errors. Quantum errors again can be leaving the quantum state or something like that.
Yeah, so I think the main challenge now in quantum computing is error correction. So this is the main problem, and I hope that researchers will solve that problem in order to quantum computing to be useful.
Yeah. Got it. So recently I came across there was a defense expo in India, and recently I came across a company who claims that they have implemented quantum secure internet. So what they said is the algorithm that they have implemented cannot be broken by quantum computers. So are there any algorithms out there?
I think you are talking about post-quantum cryptography, which is not quantum, but it's still classical cryptography. And post-quantum cryptography is still based on hard mathematical problems, which is hard to compute. And these algorithms are believed to be resistant against quantum computers. And recently, NIST will start standardization process of post-quantum algorithms and pick up final post-quantum algorithm to be deployed in our systems. Yeah.
So it's basically it's still classical, but the way you are writing it down, it's very difficult for the quantum algorithm to factorize it and break it down. Is that how it is?
So it's still, as I say, it's still classical and based on hard mathematical problems, but we don't know how to crack these crypto systems, even using a quantum computer. There are many problems that are too hard even for quantum computers, like learning with errors and lattices and many things. Yeah. But this is not quantum cryptography. Some people make confusion between the two fields, and this is purely classical, but resistant against quantum attacks, but it's not quantum cryptography. It's post-quantum cryptography.
Correct. So now it's a very naive question, totally different thing. So recently, once there was pandemic, there was a huge boom and huge talks about cryptocurrencies. Does it has to deal like what exactly cryptocurrencies are? So is there any cryptography algorithm that runs onto the backend? That's why the crypto terms comes in.
Yeah, so I guess cryptocurrencies, of course, use some cryptographic schemes, like for example, they use elliptic curve signature scheme and SHA and many other things. And quantum computing would be potential threat for cryptocurrencies if they still based on these classical encryption schemes, which are vulnerable against fault-tolerant quantum computers. Let's give an example of elliptic curve digital signature, which is used by cryptocurrencies nowadays. And this cryptographic scheme is vulnerable against quantum attacks. So maybe if we integrate quantum safe encryption mechanisms in cryptocurrencies, in that case, cryptocurrencies will be safe against quantum attacks.
Got it. So, for example, now the creator of Bitcoin, no one knows that whether the person exists or not, because it's not been long, but but because by the time we are talking about, let's say, 20, 30 years down the line, where we have quantum computers very powerful enough, and there is no one onto the back end to implement those post quantum techniques. So pretty much Bitcoin, rather than waiting for 100 years, it will take very, in fraction of minutes or hours or days, the whole Bitcoin mining will complete. Is that what you mean by that?
I mean, the security of cryptocurrencies in general, so would be threatened by the existence of large-scale quantum computers, since it's based on cryptographic schemes that are not secure against quantum attacks. But if we change these cryptographic schemes to quantum safe encryption schemes, so cryptocurrencies will be secure against quantum attacks. This is what I mean exactly. Like today's cryptocurrencies maybe employs cryptographic schemes, classical cryptographic schemes that are not quantum safe. But if we integrate quantum safe encryption in cryptocurrencies, this issue will be solved.
Got it. So pretty much right now we're talking about post quantum. Or so is there any quantum algorithm that runs onto a quantum machine, and it's not a classical thing, but it can make everything secure? So are there, because you working as a quantum computing researcher in quantum cryptography, so are there any research or any algorithm that's out there that is being implemented?
So there are many protocols in quantum cryptography, and the most successful area of quantum cryptography is quantum key distribution, where it has been established that perfectly secure communication is possible by using quantum communication. In the quantum key distribution, like keys are made of photons, for example, and quantum key distribution is already implemented in real life and demonstrated, and it's perfectly secure. Of course, we have some hardware problems. So, and also we have other cryptographic schemes like quantum homomorphic encryption, blind quantum computing, and there are some few experimental implementations of these schemes in real life.
Got it. So, so what is your role as a researcher? That pretty much so you are making these, are you cracking these algorithms? You're implementing it down. Or what exactly?
For me, I mostly recently I got interested in theoretical research in cryptography, quantum cryptography. I'm doing research in quantum cryptography beyond quantum key distribution, because maybe the most popular topic in quantum cryptography is quantum key distribution. Even I talked with some people and they thought that quantum cryptography is only quantum key distribution. Also me, 3 years ago, I did a project on quantum key distribution when I was a student, and I thought, okay, this is quantum cryptography. There is not many things to be discovered. But now, there are many things beyond quantum key distribution, like quantum homomorphic encryption, blind quantum computing, many topics, quantum obfuscation. So let's say we are trying to reinvent the classical cryptographic schemes in the quantum setting. And for me, I'm interested in theory, definitions, proofs, techniques, and I'm not a hardware person, and other people are working on real-world implementation in hardware. But me, I'm working on the computer science aspects of quantum cryptography.
Got it. So let's say if you want to explain a layman or what exactly is quantum key distribution in simple terms.
Quantum key distribution. Okay, so in cryptography we have, let's say, sender and receiver, and we have an encryption key. So we use this encryption key in order plus an encryption algorithm in order to encrypt the data. So in quantum key distribution, we will distribute these keys using quantum communication channel, these encryption keys. And these encryption keys are made of photons. So,
these are made of photons?
For qubits, or, for example, photons.
Photons, okay.
Like you
Got it.
encode your data inside your keys inside these photons, and you send them in a quantum communication channel. And in real life, that could be with satellites or fiber optics. So
Okay, so just if I have to rephrase what you exactly said, you can point it out with maybe 100% wrong. So it's basically like very similar to how classical communication works. But what you're trying to do is you have a lot of keys that you spread it across, and kind of which like based on how these algorithms work, it is very difficult to refactor all the keys, and that is what it makes it secure. So like for example, for RSA we have two keys. For this we have a lot of them. Is that how it is?
so quantum cryptography in general is secure by the laws of quantum mechanics. So classical cryptography is secure by our belief that these mathematical problems are hard enough for computer. But quantum cryptography is based on quantum physics properties, and that can offer information theoretic security. That means that the system is secure even against adversaries with a limited computational power. And in quantum key distribution, we have the quantum device and in the sender and the receiver part, and we will send our messages, our encryption keys through these quantum communication channels. And it's secure, let's say, by the laws of quantum mechanics. For example, we have we cannot copy quantum information due to the non-cloning theorem. For example, imagine the scenario that we have Alice and Bob, sender and receiver, and Alice wants to send an information to Bob, but we have Eve, which is hacker, malicious third party, and this hacker cannot copy the information, for example. Yeah, because of the nature of quantum information. In classical setting, yeah, we can. The third party can copy the information and then crack it on computer later. But in quantum information, we cannot copy. And there are many other things like superposition and entanglement, and yeah. And there's some protocols developed in quantum key distribution that can guarantee security. Yeah.
Okay, so another naive question. So is it more like because how like I'm just trying to relate with how classical communication works. It's just like you send let's say you send a WhatsApp text message or you send a LinkedIn hi, and then it goes through the like you have electromagnetic waves that travel through different different satellites and different cell towers, and then the whole like it goes to the database, and then there are like you have TCP and various other protocols that are happening. Is there ways like you were talking about, quantum communication or quantum channels over which the communication will take place? So, so these channels again have to be in the quantum space. It can be like you were talking about superposition or entanglement. So, how will this communication take place? Because attaining right now what I know is that being in a quantum state is really tough. Like even the IBM quantum stays for, let's say, fraction of seconds, and then pretty much loses its quantum state because of the vibrations and the temperature difference and all those things. So how this communication will take place?
Yeah, actually, photon loss is one of the main challenges in real world implementations of quantum communication in general, and that's why we have distance limitation. But yeah, that would be possible through quantum communication channels, through fiber optics or free space. So we use some quantum devices, and yeah, there is quantum communication channel between the sender and the receiver, and we can send the photons, and we encode our data inside these photons, and these photons are polarized. For example, if you have one, you can polarize this photon. They have this polarization. If I have zero, they have this polarization. Yeah, this is just random thing. Just an example to explain. You have the data and you encode it into qubits, and then you send it through quantum communication channel. Yeah.
Got it. So pretty much, are there any real world implementations of it yet, or we are still into the research stage as of now?
I think yeah, there are some implementation that connect some research labs between each other. So it's not, let's say, implemented in large scale So like for only for quantum internet is implemented between some research labs for very short distance. Yeah, it's still in research, I guess. Yeah, it's the.
So let's say if I want to get started in quantum, so is there any tech stack that you're following which I can look onto or get started with for anyone new to quantum?
Okay, so for someone who is new to quantum computing, the first thing to start with is to learn the basics. There are many online resources, and then learn or being involved in some activities and some research projects, getting internships, and there are many non-profit organizations that give let's say mentorship and supervision for research projects like Keyword and the Quantum Open Source Foundation. So many students can participate in that programs, and that really help. Also participation in workshops, hackathons. Yeah, so for beginners, that would be very useful to do these kind of things. Start learning. Also, it depends on the background of the person. But we need some background in linear algebra, bit of background in quantum mechanics, and computer science, of course. Yeah. And then you can pick up a topic and do research in some specific topic. Because it's a huge field and very interdisciplinary. There are many things to do. Some people have background in chemistry, in engineering, computer science, and many things, physics. So it depends which field you will do research in afterwards.
Got it. What keeps you going, Mohammed? Is it like I'll let you answer that. Yeah, I don't want to give directions. Yeah,
I'm really very passionate about this topic, and I'm excited to do research in quantum, especially in theoretical quantum cryptography, which is my niche research interest. Yeah, so this is actually my motivation. Like I'd like to do research, and since I was young, my dream is to become a scientist. Yeah, and the quantum computing is my field. I mean, my passion.
No, because the reason I asked this question is because for let's say being as a tech guy or being deployed or deploying solutions, pretty much there is a sense of achievement once you complete the project. But once you're researching, you don't know whether that research will be actually fruitful in the end, or whether you will get those positive results out in the end that you were expecting it to work. So that was the main motive behind that.
Yeah. And it's really excited to contribute to this field that will change the world. Maybe.
Rapid fire round.
And
yeah. And it's a small rapid fire. It'll be 3-4 questions. Let's go I'll be asking you rapid fire round.
Okay.
Couple of questions. It's a small rapid fire. It'll be 3-4 questions. Pretty much you can answer them. Asking you like you have to answer them, or you can also defer them and a kind of reasoning in the end. Pretty much you can answer them. So pretty much will be very simple for you. You can also either quantum or AI. A kind of reasoning in the end. Like why is that? Which one would you choose? Pretty much will be
absolutely
very simple for you. It's either quantum or AI. No doubt about that. I don't even want to know why is that so. So next question is Python or C++?
Python. Python because in quantum computing we use Python a lot. So
next question is Python or C++? But isn't the backend written in C++?
Python because in quantum computing we use Python.
Isn't the backend written in C++? But isn't the backend written in C++? Half few modules are written in the backend. Isn't the backend written in C++ or C?
Yeah, also some quantum programming languages are written with C++, and I believe C++ maybe is more powerful than Python. But for me, I would like to use Python. I'm more comfortable with Python. But C++ is more Python. But for me, I would like to use Python. I'm more comfortable with Python.
My next question to you is: you being the researcher, do you like speed or do you like perfection? Speed in the sense. My next question to you is: do you like speed or perfection first? Then I'll go a bit more into perfection. Speed in the sense. Perfection. If any, okay. Do you like speed or define perfection according to you, and define speed according to you?
Perfection.
Perfection.
Speed maybe doing
define
many tasks in short amount of time.
According to you.
Perfection doing something outstanding tasks in short amount of time, but without limitation in time. If you perfection compare brings it to speed.
Okay,
something
so
outstanding,
for me, speed was trying out
but
different
without
experiments.
limitation in
Like
time.
let's
If
say
you
if this
compare
will
it to
not work,
speed.
let's try this. Let's try this. Let's try
Okay,
this.
so
Let's try
for me,
this.
speed
Maybe it
was,
cannot
trying
be
out different
perfectly executed,
experiments.
but you pretty much gets an idea of it that okay,
let's try
this is something that we can
let's try
explore
this.
more in
Maybe
depth.
it cannot be perfectly executed.
And perfection is, you
pretty
take
much
one and
gets
gets an idea of
give
it
it all
okay,
and say, okay,
this is something that we can
cannot be
explore
done.
more
This
in
is how
depth.
it has to be done.
And perfection is, you take
Yeah,
one and
if you do something
you give it all
perfect,
and say, okay,
nothing is
this
perfect.
cannot be
But if you
done.
do
This is how
something
it has to
perfect,
be
that
done.
would be great.
Yeah.
If you do many things,
something
with the speed
perfect,
and
nothing is perfect.
with bad
But
quality,
if you do something perfect,
yeah, that would be very bad.
great. If you do many things
With the speed
So,
and with bad
are
quality,
you hands-on?
yeah, that would be
So,
very bad.
And you do code. So,
yeah,
are
of course.
you
Yeah,
hands-on?
I did
So,
love coding,
and
especially when I was
you do
studying.
code.
Even now, yeah, I like
of course,
to, I like to do research and theory, and also implement I was studying things. So even now, I like to.
So,
I
a
like to
follow-up
do
question on
research and
that. Like,
theory, and
what do you
also
implement it on? So it's pretty much Python because you've
things.
chosen
So, yeah.
Python. So,
any
a follow-up
libraries
question
or
on that,
frameworks
like,
that you use?
what do you implement it
So
on? So it's
before I
pretty much
used
Python because you've chosen
Qiskit,
Python.
which is software
So, any
development
libraries
kit.
or frameworks that you use?
Yeah, we can, let's say, program quantum computers using Qiskit. Also, I used Simulacron, which is quantum neural net simulator developed by QTech. Program quantum computers using Qiskit. Now, mostly I use Qiskit to simulate some quantum neural net simulator developed by QTech. So
have you used TensorFlow Quantum?
I use Qiskit to simulate
TensorFlow
some
Quantum.
cryptographic schemes. I used once,
Have
but
you used TensorFlow
I'm
Quantum?
not really expert with TensorFlow Quantum. I only explored once, but I'm not really expert with that.
No, the reason I asked is because
I only
I've reached out to the founder of TensorFlow Quantum for this podcast. No, the reason I asked
So
is
he
because
is yet to reply, so
I've reached out to the founder of TensorFlow Quantum for this
if he
podcast. It will be really nice, but so I was like,
he is yet to reply.
Let's say the reason for me before I was interested in
if he comes, it will be
in many
really
topics
nice,
in quantum, including quantum machine learning. But now I guess I know what topic I'm interested in. So I'm not like quantum machine learning is not my primary research interest. So what topic I'm interested in. So I'm not going to use like TensorFlow Quantum or any other quantum machine learning framework too much. I'm not expert in this topic. I'm not going to use TensorFlow Quantum or any other quantum machine learning framework too much. I'm not expert in this topic.
So tell me about Q-Tunisia, like what exactly it is.
So Q Tunisia is a community, non-profit community affiliated to Keyword, which is an international, say, non-profit organization that gathers researchers, developers, and many also business people in one place. So Q Tunisia aims to, let's say, popularize quantum computing in Tunisia. So basically organize workshops, talks, and in order to encourage people to be involved in quantum computing and to raise awareness about this field.
Got it. So it's basically pretty much like, you're building a community out of it. And a lot of the more people come into, the more faster the tech grows. Yeah, makes sense.
Yeah. So just encourage, just to encourage people, I mean, to learn quantum and to support them.
So thank you so much, Mohammed, for joining in. Pretty much, it was really I learned a lot of new things about quantum, about post-quantum, about the quantum algorithms that are right now being in the research phase between the laboratories testing it out. And thank you so much for your time. And I hope even the listeners listening definitely learned something from this podcast. Thank you so much.
Thanks so much for inviting me, and it's a pleasure to be with you today.
Awesome.